Questions before we get to the ski problem? Because we could have solved that using the stuff we got from chapter 3. But now, the problem that's much more difficult with chapter 3. That's my idea of a skier. And I want to know how fast he's going at the bottom. So let's take a look at the forces acting on him. I'm going to pick some point. I'm going to pick, say, the spot right here. And let's do the forces acting on him at that point. We assume the reason why we're doing a ski problem, we're going to assume that the friction is minimal. So we'll just say that the coefficient of kinetic friction is 0. So frictionless.
What does the blue say at the top?
What's the blue say at the top?
Like, what is that? What is that?
That's just drawing of the object. We're going to do a force diagram of the person, so I just drew the person there. We're going to draw arrows, but apparently blue's not doing it for you.
Why was friction NK?
That's mu. The coefficient of kinetic friction is a shorthand notation for saying that there's no friction while he's skiing.
No, okay. I should know why it was N. So I was thinking of N.
So it's supposed to be a mu.
Oh.
What are the forces acting on him as he's at this point in the slope?
No wrong force.
Okay. Yep.
Are we not drawing it on a slope here?
Say that again?
Like up from this slope?
Oh, there is. I only care about the forces acting on him.
On him, okay.
All right, that's it. No friction, no tension, no other. Weight, conservative or non-conservative? All right, normal force, conservative or non-conservative? That was nice. I appreciate the unison. All right, it is non-conservative. So, suddenly are we dealing with a horrible problem here? Well, let's take a look at the work being done. Work is force times displacement, dot product. At this point, in which direction is he moving?
To the right.
That way?
Or down. Go down.
Okay. All right, he's moving that way. Which way is the normal force? So we've got normal force and displacement in perpendicular to each other. So what is the dot product of things that are perpendicular to each other? Flashback to an hour ago. Objects are, if two vectors are perpendicular, what is the dot product?
Cross product?
Dot product.
No.
So we doing a multiply?
What's that, Jennifer?
Multiply?
What is dot product multiplying? Okay, in fact,
Two
what parts of the
vectors?
vector?
Parallel.
Okay, so if two vectors are perpendicular, what is the dot product? Gut feeling. The squaring is if it's in the same, the vector multiplied times itself.
The I hat.
So if I've got, let's do it in terms of I hat, J hat. I hat, J hat, sticky marker. If I had 4 I hat, not 3 I hat, what do I get?
12.
4 I hat, not 3 J hat.
Still 12.
It is not.
Oh. Isn't it the same?
It is not. Let's see. Back to. I think it was around here. Yeah, when we multiplied B times A, this B times this A, we multiplied the parts that were in the same direction. And I got nothing to the J, so it'd be 0 times 2, then 4 times 3. That's why it was 12. So if I'm supposed to be multiplying parallel parts and they are perpendicular to each other, what do I get?
You get 9. No, because you multiplying the. Oh, no.
Right, let's look at this a different way. I have a vector here and a vector there, and I'm doing a dot product. If I had so let's imagine I got 2 pieces of wood. And I have a light above it. This one is going to cast a shadow onto the other one. So it's going to cast a shadow, and that shadow is basically going to be, with an overhead light, shadows right below it. So I'm going to multiply the length of the shadow times the length of the other vector. In math, it's known as projection. So when I'm doing a dot product, I multiply basically the shadow times whatever the shadow falls on. If I have a vector that's perpendicular to another vector, what's the size of the shadow?
9. Well, is it 90 degrees?
If that's 90 degrees, and I have a light overhead,
Let's see, like 100%, like this light would be all over?
the shadow would,
There'd be no shadow.
okay. no
That's what I
shadow.
meant to say, yeah.
No shadow. So, if I'm multiplying the length of the shadow times whatever it got projected onto, if there's no shadow, what's the product? The dot product?
0.
Yes, 0. This would be 0. Where we were. Oh, we're doing scoot. There we go. So, if the normal force is perpendicular to the displacement at that moment, what is the work being done by the normal force? Hint, it was the same answer as the previous question.
It's 0.
0. Yeah, if this is perpendicular to that, there's no work being done. Look at it a different way. If I have an object that's moving, so I'm going to move the table. The force that am I helping it move or trying to stop it moving? Okay. If I'm helping it move, then the work that's being done is positive. Because part of my force is in the direction of movement. Now, you got a runaway car coming at me, and I push on it, so I get pushed backwards. Am I trying to help the movement or hurt the movement? So the work I'm doing is negative. If the car is careening down it, and I'm standing on the roof pushing down on the car, am I helping or hurting? Or neither?
Neither.
So no work is being done. If you make it go faster, if your effort is trying to make it go faster, positive work. If your effort is trying to make it go slower, negative work. And if you're not helping making it go faster or slower, no work, zero work.
So is that what you're saying in this problem is
Yep.
what would be the zero work that's like acting on, you mean like gravity?
The normal force is not doing any work.
Oh, the normal force isn't doing, okay.
Yeah. Which is fortunate because it's a non-conservative force. But because the normal force is not doing any work, the non-conservative work is zero. Which means all we're left with is conservative work. In other words, energy is conserved. Which is what we want. So if I know the energy here, I know the energy here. So my initial energy is equal to my final energy. Well, I have two types here. I assume he's not bursting into flames. So I just have my kinetic initial plus my potential initial is equal to my kinetic final plus my potential final. What about to ask that question again? What's the formula for kinetic energy? Done in rounds. So 1/2 mv initial squared. What's the formula for potential energy?
Which one?
Thank you. The one associated with weight. And then just the same stuff with the final. mv final squared plus mg final plus c. The c cancels out. And oftentimes we don't bother writing the c. All right, I did not tell you his mass because it really doesn't matter. Every term has mass in it. So I can just divide out by mass. So the mass doesn't matter. So what I've reduced this down to, 1/2 v initial squared plus g h initial equals 1/2 v final squared plus g h final. Bunch of letters, let's see if we can narrow it down a little bit more. All right, so let's have him start at rest, or it's close enough to rest. He's just teetering on the top of this, on the precipice, and then that lands on his back, which is enough to get him to start to move. So his initial speed is close enough to 0. I'm trying to figure out the final speed. So we need to establish height. What is his initial height?
50 meters.
What assumption did you make?
The ground is 0.
Yes. And typically, you either want to make the beginning of the problem, the height is 0, or the end of the problem 0. So we're establishing height is equal to 0 there because we say so. So final height is 0. So now we're left with just GH is equal to 1/2 V squared. So GH initial is equal to 1/2 V final squared. So that's 9.8 times 50 is equal to 1/2 V final squared. So this would be 9, 8.
$31.3.
Thank you. Get it? questions up to here?
How did we get 30 back? What the 980 would be? This is square root of 980?
Yeah. Yes.
Oh, and then the 1/2, where did it go?
Oh, yeah, I multiply both sides. So if you multiply those together, you get 490. And then I multiply both sides by 2. So if I multiply this by 2 and this by 2, that 2 cancels out with the 1/2. And then I have 2 times 490, which is 980.
What did you do to the 980 to get to 31.3?
So 980 is the speed squared. We have to get rid of the square. And the way you undo a square is the square root. So if you then take the square root of both sides, this just becomes VF, and that is 31.3. Unless my sources apply to me. Sorry, I'm about to change the problem slightly.
Can you go back to the picture really quick of the? So do we always have to do a force diagram in these questions?
You need to be aware of the forces involved. So
Okay.
whether I explicitly ask for a force diagram or whether you just
So
look at
since
it,
now, since now we know, like, normal force is not conservative and equals 0.
it doesn't do any work.
Yeah, so that's how we know if we can 0 for that.
Yeah.
Okay. And like if something were pushing him,
Then, that's why,
Then-
yeah,
it wouldn't be,
correct.
okay,
Then, yeah, you would have, the total, these would not be equal to each other in that
okay,
case.
okay.
All right, let's just keep this here. So we had, this was 31.3 meters per second. So, skier comes down to the end, like so much, goes back up to the top. Takes the ski lift, whatever happens. What he doesn't realize is that there was a cave in. So I am gonna go out to. It's still 50 meters up here. There's a cave in now. He comes back up to the top, doesn't realize there's a cave in. He starts skiing down. So the question is, how fast is he going when he gets down to here? Someone want to take a shot at it before we talk about it?
So the cave-in looks like it's about halfway.
Okay.
50 meters.
The cave in's about,
Huh?
you said cave in's about halfway, what, from start to this way?
On the 50 meters.
Okay. I will tell you that even if you said 2/3 of the way, or 1/3 of the way, or 1/2 of the way, the answer's not gonna change.
You mean like the speed's not gonna change?
Correct.
Even though, if there wasn't a cave-in, wouldn't he slow down in that area?
Yeah, but then, well, he would speed up till he got to here, then he'd slow down some, then he'd speed up again.
Okay.
We are ignoring air resistance.
So I feel like if you fell in the cave-in, you'd be going faster, right?
Faster than what he did the first time?
Yeah,
He will not.
no,
Therefore, how fast is he going when he gets to the bottom of the pit?
31.3 meters per second.
This is a big plus with energy is, now, the velocities are different, but the speeds are not. And when he gets down to here, he's going 31.3 meters per second. Now, the skier's not hurt, because at the bottom of this, we have clouds, kittens, and cotton balls. He lands on it. The kittens show him the way back up to the top. Comes back up to the top. While he's scrambling up to the top, it snows, fills in this legally again. But meanwhile, while he's climbing up to the top, the owner of the ski slope decided to put a giant spring in at the bottom, as ski slopes tend to do. Or tend to have, I'm sure, it's been a while. And so he's gonna come down all this way, he's gonna hit the spring, and he's gonna compress the spring. So now, he's gonna compress this ideal spring, and the question is, how far will it compress? We still have, so if it's an ideal spring, and I've erased it, it was written over here. If it's an ideal spring, then it's a conservative, it exerts a conservative force. And therefore, we have a potential energy formula for it. So he's going to start out with all this gravitational potential energy. As he's going down the slope, the kinetic energy is going to rise and fall depending upon where he is on the slope, but ultimately, he's going to lose all that gravitational potential energy and have all this kinetic energy. The spring has no elastic potential energy until he hits it, and as he hits it, his kinetic energy will start to drop, the potential energy of the spring will start to go up. And when he's out of kinetic energy, we're at the maximum compression. We do need to know his mass at this point. Actually, let's take a break here, take a 5-minute break, come back, and then we'll tackle this and clean up the picture.